Hello, welcome back to the maintenance course. Today we have a fresh new topic coming out of the oven. We will talk about predictive maintenance. And what is predictive maintenance? We will try to answer this question in this lecture. So if you're curious about it, stick with us and thank you for watching. Today we have 4 topics of interest included in the table of contents. We will start, as usual, by the beginning, by the introduction to predictive maintenance. So let us start. In the beginning, there was maintenance. Then there was preventive maintenance, and then someone came up with the idea of predictive maintenance. That's the whole history of maintenance, of the modern maintenance in a nutshell. But let us see this in more detail. So in the beginning there was corrective maintenance, which was essentially the idea that maintenance could occur after failure. So you would let the failure occur, perhaps with some redundancy in the systems, and then the maintenance would take place. But this had high costs, because every time that you would let the system fail, this would incur in costs. Not good. So the idea was to invent something that we call the preventive maintenance that would look into the past with statistical ideas and would make predictions to make time-fixed schedules of maintenance, to establish a schedule of maintenance. And this was the idea of preventive maintenance, which was a much more proactive strategy than the previous one. And then someone thought, what if we did maintenance only when it's needed, only when it's really needed? And then we invented the field of predictive maintenance, that is perhaps the most advanced in terms of technology, and the one that aims at the lower costs. That was the idea of predictive maintenance, and this was essentially the evolution of the maintenance strategies over time. This doesn't mean that we only have predictive maintenance nowadays. That's not true. We have corrective maintenance, preventive maintenance, and predictive maintenance for different systems and for different occasions. And that's the beauty of it. It's like a symphony of strategies that we need to handle in order to have the best possible maintenance of all our systems, at least in aeronautics, of the aircraft in this case. But how do we do predictive maintenance in the first place? How can we define predictive maintenance, and what defines it, what characterizes it? Well, predictive maintenance is based on the actual health status of the equipment. So the idea is to look at the system. It has temperature, it has a vibration, it has a current, it has an humidity, according to the type of system. We analyze that, and based on that analysis, we come up with an estimation of if it's a failure or not at the moment, if we are close or not, and how long it will take until failure actually happens. The fundamental idea behind all of this is to reduce the total life cycle costs, because it doesn't make sense to do a maintenance strategy if it doesn't reduce the costs. So we are aiming to reduce the costs and to have more benefits with this strategy. And the set of technologies behind the predictive maintenance field is what we call the Prognostics and Health Management, PHM. And PHM is essentially the technologies that will enable us to do predictive maintenance. So it has everything like physics, data-driven, machine learning, statistics, a lot of technology that we need to do predictive maintenance. So the goal essentially is to predict how we're going to be in the future in terms of the system, based on what we know now and what we know in the past. So it's not just about the past, it's about the now also. So it involves a lot of different strategies and disciplines. Like, for example, you have to place sensors in the system, so we need to know how to place them. We have the concept of physics that we need to integrate in our models. There are techniques from machine learning that can also help us. And of course, we still resort to statistics and reliability engineering in some of our models, in some of our modeling strategies. You have never seen graphs like this, right? At least until now. This graph is beautiful in a certain sense because it shows the evolution of condition monitoring signals, like the temperature of the high pressure compressor of an engine, or the vibration of another element of the engine. And all of these condition monitoring signals are going downwards, showing us degradation over time. And we can use those trajectories, we call it trajectories, to be able to forecast the future and to say, are we in failure and when are we going to be in failure? And that is the idea of prognostics and health management and predictive maintenance. In prognostics and health management, we talk about two things, the now and the future. The now is diagnostics, the future is prognostics. Let me explain. So in diagnostics, we try to identify if there's a current problem at a certain moment based on the condition of the system. In prognostics, in turn, we don't care about the now. We care about the failure, about the future. So it involves predicting based, again, on data, on monitored data, where the system will be in the future, and if it's going to be in failure or not. So over time, from now until failure, what is going to happen? And that is prognostics. So there is this fundamental distinction between the diagnostics and the prognostics. So diagnostics is to use classification of what is happening today and the causes of degradation, while prognostics is to look into the future and to say, haha, in 10 days there is going to be a failure. And that is prognostics. When we were talking about preventive maintenance with the stochastic modeling and the Weibull distribution and all of those tools, we were talking about statistics. So the approach was to use statistics to do preventive maintenance, to define the fixed time intervals. In predictive maintenance, we have three fundamental approaches. The physics, where we use mostly physics to understand when the failure is going to occur. The data-driven model that uses machine learning and artificial intelligence. And the hybrid modeling that uses a mix of physics and a mix of data-driven. Starting by the data-driven models, we have two possible sub-approaches. We can be based on statistics, or we can be based on artificial intelligence techniques, such as, for instance, machine neural networks or random forests, and so on. The training data that we use to create a data-driven model is based on failure event data, so we need to know when the systems in the past failed. But we also need to know sensor data. So for those systems that have failed in the past, how was the condition in terms of pressures, temperatures, vibrations, and so on. With this, we can create a mathematical model which is more abstract than, for example, the physics-based models, and try to predict what's going to happen in the future or classify what's happening currently in the moment. Physics-based approaches are different because they can rely just on sensor data. They can use failure event data, but they don't necessarily need to rely so much on the failures because they have a physical model of degradation. The hybrid approach is in between the data-driven and the physics-based approach. And it also uses failure event data and condition monitoring data, sensor data. And the goal is to create a mathematical model that includes physics knowledge. And that is essentially the three models that we have in Prognostics. In fault diagnostics, we need to give a lot of information, such as we need to show what is the equipment state at the current moment. If it's failed, what is the fault mode and the fault location, and other characteristics of interest. And it's always based on the condition of the system. So we need to monitor the temperature, the pressure, the acceleration of the system, and based on that we use what sometimes we call classifiers to find different classes of failure and different classes of information. And we have here an example of a classifier, and it's very complex, I know, but it's essentially just to show that in the end it's doing diagnostics. So it has this half of a circle showing if the system is healthy, medium degraded, or if it's faulty. And that's essentially the idea of classification and of diagnostics. Regardless of the complexity that goes before, in the end we have 3 states or 4 states or whatever states that gives us information about what is happening now. In regards to the process of diagnostics, we have several stages, from data collection to fault classification and fault isolation. I will explain each of them in a few minutes. The first step of diagnostics is to perform data collection. And in data collection we need sensors. You can have more sensors or less sensors in the system, but you need real-time information from those sensors, from those monitoring tools. And it's like an investigator that tries to collect observations like temperature readings, pressure levels, or any other kind of relevant metric to its investigations. Before we have the data, sometimes the data doesn't come with the best quality because we cannot put the most costly sensors in place in a system. And to ensure the quality of the data, sometimes we need to pre-process the data or to process the data. And we need to remove things such as outliers or noise or any type of missing data or any data point that is not going to do us favor. There are many different pre-processing techniques, but I'm going to talk about one that is really important, that is to feature scale. And to feature scale means that if you have 2 features, the temperature and the pressure, you need them to be in the same scale. So if the temperature goes up as high as 500 and my vibration never leaves the range of -1 and 1, then I have a problem. So I need to put them on the same scale. There are 2 techniques to do this, the min-max normalization and the standardization. And we always apply the feature scaling to a feature, a single feature. So I apply it to the temperature and then I apply it to the pressure, to the vibration, sorry. So min-max normalization is to get all your values of temperature or all your values of vibration, take the mean value and divide by the difference between the min value and the max value. And that's essentially, it's going to put your data between 0 and 1. The standardization, it puts your data with a mean of 0 and a standard deviation of 1. So it's a little bit different. Standardization scaling, also known as the z-score normalization. Remember the z-score? We use it here also. We sometimes call it z-score because we also employ the mean and the standard deviation in the calculation. And we put it in a standard scale with a mean of 0 and a standard deviation of 1. That's where we put our data. Unfortunately or fortunately, the standardization changes the values a little bit because we're trying to put the mean on 0 and the standard deviation on 1. So we're squeezing or enlarging a little bit our points. Because we want the distribution standard deviation to equal 1, we have to do this. But this can actually help some models, such as neural networks. In some occasions, you actually see this working very well. Min-max normalization is a linear transformation. So importantly, it will preserve the relationships between the data values. When I scale the temperature, when I scale the vibration, I lose the least amount of information and I get the scaled data in the range of 0 to 1. And we have here an example. We have 5 data points and we're going to transform them into a normalized scale from 0 to 1. As you can see, the distribution of the data points stay the same, you just change the scale. But when you standardize, because you want a standard deviation of 1 and a mean of 0, the distribution changes. After we have done the pre-processing, we can detect the fault. And what is fault detection? We just have to see when the behavior is deviating from what we would expect. We can do this in many ways, such as, for instance, with thresholds, with statistics, or with machine learning. But the goal is always to target the failure, to know when it's happening, and to not give false alarms. After the failure is detected, once we know for more or less certainty there's a failure, we have to classify it to understand its nature. We have to classify its severity, for example. And after we classify it, we have to do fault isolation, where we say that's the cause of the failure, and it is located in this place. And that's the fault isolation step that finishes the diagnostics process. Let us now discuss prognostics. In prognostics, we care about two concepts: the concept of end of life and the concept of remaining useful life. And they are interconnected, because when I'm a certain point, the point that the distance between the end of life and my point is the rule, the remaining useful life. And essentially in prognostics, we try to predict the rule. And what is prognostics' core idea? The idea in the simplest shape is to have a single feature, such as a temperature, and imagine that it's going upward. Then you can extrapolate the trajectory into the future. Once it reaches a given threshold, you know that that's the predicted failure, which can be different from the actual failure point. But essentially this is what we do. We try to extrapolate what's going to happen in the future. Maybe we set a threshold, or we somehow identify that there's a point of failure, and then we calculate the rule, the remaining useful life, how long it takes until failure. Of course, in reality, this is not one-dimensional. We have several features, and the problem becomes much more complex. If I know that a failure is going to happen in advance, I can have several benefits, or I can take several benefits of it. Such as, for instance, we have a better scheduling because we know exactly when the failure is going to happen, at least in theory. We can do an optimal planning of spare components, of spare parts, so this affects logistics. We can have less spare parts in the inventory management, and we can also control the system to avoid something from happening, such as a failure. Prognostics is a process that has many sub-steps according to the author or according to the modeling approach. But I'll give you the major steps here. So first we typically start with data collection. Then if the data has low quality or it's not as we want, we do some kind of pre-processing. And then we extract features from it. We can do some kind of physical smart extraction here. Then this is going into a model, such as a machine learning model or a physics-based model or a hybrid model. And after we gather the predictions, sometimes we need to make sense out of them by applying a Kalman filter or by doing any other kind of post-processing technique. Finally, we have the decision support system that is fed with this information to make its decisions in a better way. And why does Prognostics actually works? Well, it works because we know that degradation follows the PF curve, and the P stands for potential failure and the F stands for functional failure. The idea is that if you have a system degrading, the condition of the system will decrease and it will reach a point of potential failure where the degradation starts to be much quicker. And that's the P moment. After the P moment you go down until the end of life, or in other words, until the functional failure. And that's the moment where you know that you should take your system out of functioning. And this is essentially the idea of the PF curve that tells us how a system degrades. And as you can see, it is predictable. So if it's predictable, we can apply it in prognostics. An example of the behavior of the PF curve is to have an engine. And you have an engine and the fault, the point of potential failure, is the initial crack. The compressor is still within tolerance, but you can still see the effects. So you have a high increase in vibration and you have less efficiency of the engine. The failure will only happen, the point of functional failure will only happen when the crack reaches a side that violates the functional constraints. And in that case you can see excessive vibration and violations of stall margins. And that's the idea. You start with a small fault, then it develops into failure, and you have to take the system out of operation. And we can see the PF curve, the potential failure and the functional failure in real sensor data. So we have the CMAPS data here, which is the data of a simulated engine. And you can see different sensors. And in all sensors, except for the flat sensor, you can see that you have first a healthy period until the P point, and then you have a more rapidly degradation afterwards, ending in the functional failure. Operating conditions and the detection of the operating conditions is very important for prognostics, because according to how the system is operating, that can mask or not the degradation. And if you have, for example, initial conditions that are more favorable, you may last longer, while if you have more severe conditions, you may last less. One example of how operating conditions may mask the degradation of the system and may not allow us to see the PF curve is the following. So you see here for different sensors, you see here the signals, and because we are jumping between flight phases, you cannot see so much the beautiful PF curve that is underlying. But there are techniques that we call baselining to show the PF curve that is underlying the original data. And we are now at the fourth section where we'll discuss two case studies, the CMAPs and lithium-ion batteries. CMAPs is a simulation of an engine that was used to simulate degradation of several engines. The data is also called CMAPs data, and it includes 4 different data sets. Each dataset has a different combination of operating conditions and of fault modes, and several sensors record the evolution of the fault. And importantly, the data was provided by Prognostics Center of Excellence at NASA. In the data, we can see the trajectories of different engines for different sensors. So as you can see here, each colored trajectory is an engine, and they have different endpoints, different end of life. And the goal is to try to predict at a certain moment how long it lasts until failure. That's the entire challenge. This is a list of some of the works and proposals of models for the CMAPs. And you can see that the more you have in complexity, the less you have in terms of error. So the accuracy increases the more sophisticated is the model. But we can also analyze other systems, not just the engine, such as batteries. And for example, you see here a trajectory of battery discharge over time. And why do you need predictive algorithms if it looks that it's going downwards linearly? Well, we need it because in the specific case of the battery, it's going downwards exponentially at some point, following the PF curve idea. So if we would expect it to grow linearly, we would have a large prediction error. So we need to be able to use more advanced methods to do prognostics on batteries and in most systems. I hope that you have enjoyed the lecture, that you are now more acquainted with the topic of predictive maintenance, and that you continue watching our lectures and our videos. So thank you for watching again, and see you next video.